In any case, this is a new topic for us. I'm investigating this relationship between processing, structure, and properties. It's a very large subject. We deal with it in three parts. You have to deal with the rheology, you have to deal with the structure that you end up being able to manipulate with the rheology. And then today we're going to focus on what happens if you, how about the resistance to cut? So the fracture mechanics. So this is, for us, is a new topic. And we are motivated by having sustainability, but the sustainable polymer typically are poor in properties. So we are in the business of trying to figure out how we can help. So here is the summary, really, of what this talk is going to be about. Well, I have this big picture of what the polymer mechanics is. There is the rheology part. There is the part dealing with solid state polymers, either glassy or semi-crystalline. And then if we have some answers to them, then there will be a last topic, which is fracture mechanics, that I'm going to focus on today. In fact, on this second episode on crystalline polymers in terms of mechanics, there will be a talk tomorrow at exactly the same time in the crystallization section tomorrow by Travis, my student. So in any case, we know rheology, we know fragility, we know how it changes with temperature. We know it's a chain network if molecular weight is high. We know that chain network, when you cool down to glassy state, is still there. In addition, there will be entrapment due to vitrification. And we have a lot that we think we understand in terms of how to answer the question of why a polymer can turn from ductile to brittle in absence of any cut. So I'm going to skip all this. It's something we published, we know about. So let's move on and, oops, sorry. And look at fracture mechanics. Well, it's a very old subject for polymers as well, the books written. The foundations of fracture mechanics is something that I summarized here. It's basically standing on two pillars, either the energy balance approach or the so-called stress intensification approach. Both of them have a great deal of difficulties that I have not enough time to expand on. But since this probably is recorded, I give you this busy slides asking questions. You know, what determines the mechanical strength? Where does fracture mechanics comes in? How can we improve toughness? So on and so forth. There are so many questions here. So in short, I would say that fracture mechanics, of course, is a way to give us a coherent description of phenomenology with regard to fracture, but it doesn't really suggest any molecular strategies. So this is why I think there should be a marriage between the episodes of molecular mechanics and the episodes of fracture mechanics. This goes on, and I only mentioned briefly a difficulty with the fracture mechanics in the sense that we find that the measured energy release rate is orders of magnitudes higher than the theoretical estimate of what the surface fracture energy is by 4 order magnitude. Textbook says 3 order, I can say it's even more. And so it's not so easy to brush this problem away by saying, oh, there's plenty of plastic process going on, so you are not dealing with an ideally fractured brittle material. Well, I will leave that subject for future discussions. And once again, there are really plenty of questions to bother us with. You know, is really this fracture mechanics approach good enough? Does it really capture? How do we evaluate this critical energy release rate? Where do we find strategy to toughen our polymer? So the list goes on and it's the first time we are working on the subject, so tons of questions come to mind. Perhaps we are just ignorant, we're beginners. Some question we don't, people think they have answers, but we have yet to find them. And in addition, I don't think we fully understand all this, honestly. I hope to convince you of that today. So for the remaining precious amount of time, let me give you a summary of 3 types of phenomena that I personally don't find them possible to explain using textbook knowledge or state-of-the-art understanding from fracture mechanics. Okay, so these are 3. I have however amount of time left. How much time, David? Probably 8 minutes.
You're at something like 6 minutes or 6 to 7 minutes right now.
Okay, gosh. So in any case, then I have better get going. So there are 3 types of phenomena. We're going to look at them. Each of them is peculiar. This is the first one. We were crazy enough to look at the samples of different lengths and with a cut, and find that the samples longer will fail brittly. Watch the right figure, and the sample shorter will fail ductily. Well, we have no time to give you all why we think this is the case. So let's look at this problem a little further by taking a piece of polymer that can give us nice birefringence with a cut. And here are the 2 movies showing that the long ones break, the short one does not. This is and this is the SS curve for that. This is rather strange already. How come the length comes in? Because in the general discussion of fracture mechanics, this length will not come in. Moreover, let's move on to the second topic. It's even more bizarre. Take a sample that's cut-free. Okay, we're going back away from fracture mechanics. It's the normal thing we used to deal with. A sample that's cut-free. Well, similarly, we find that if the sample is short, it will be ductile. I know this movie played fast, so there is a point it yields and it shows this red curve. But the long sample, this movie is supposed to be showing, it has 2 movies. Let me just get to the point. The long movies, the one is a regular speed, the other one is at high speed, so you can see the failure around here. It's brittle. My goodness, this is completely madness. Just based on different length of your sample can turn, here's that movie, can turn from brittle to ductile and vice versa. So given the amount of time that I have, let me go to the third topic, which is even more bizarre. A sample, we find it to be brittle if there's no cut. And once you introduce a cut, your sample turns ductile. Okay, so this is a fast speed movie, so I better just go to the last part and see how it fails. I can convince you it's brittle. Just watch it a little further. And okay, it's brittle. And this one with a cut, it's ductile. And you see this movie showed you. This is a beautiful birefringence, just reports for you all the local stress field, strength field, so on and so forth. And my goodness, by introducing cut, I have made my polymers much more tougher and more resistant to high strength without breaking. Is that always the case? Well, it turns out it's not always the case. Now, those movies were for PET. Here's a movie for polystyrene. Okay, when you look at polystyrene, indeed it agrees with what I used to understand, that without cut it's brittle, with cut it's even more brittle. How can it not be? So we dial up in this movie the load more and more until it breaks. Okay, until it breaks. And this is just a, be patient with me, this is just a fast speed camera showing the same. I know it's, okay, here it is. It breaks in a very small fraction of a microsecond. And if you like, lastly, you can do it 2 ways. You can have the brittle failure without cut, or you can have a cut that's so tiny that it is still brittle. Okay, so look at the second movie, boom, it breaks. But if you introduce a bigger cut, now it turns ductile. Let me play that, then we're done. So when you have a bigger cut, the ratio is 0.1 now, it's ductile. I have no time to go into how we think about this, explaining this, but to draw the conclusions for you for now. Really, to really have a sense of mechanical strength, we need polymer physics. Because the fracture mechanics doesn't address the molecular aspect of it. And so we're trying to figure out what part we can inject some molecular level understanding into the fracture mechanical problems. And we found three rather peculiar sets of phenomenology or phenomena, if you like, that are challenging textbook understanding. And certainly we are working very hard to this is just the very beginning phase of what we're trying to learn and to establish some bridge between fracture mechanics and the molecular mechanics that involves no cut. I think I'm doing okay with time, right, David? I'm done.
We're out of time. Yeah.